Hello and welcome to this session on setting up a free flow simulation involving heat transfer between the SPH elements, the fluid, and basically the wall around the fluid that's represented by the SPH elements. So here we have imported modules for the SPH. So the modules are basically, and I can show all the ones that are available. So I imported the boundary interaction statistics, the density, the HTC module, very important if you're modeling heat transfer, and the mass flow rate module. For physics, we have gravity in the negative z direction, and we have basically the default fluid, which is representing water, and that's what we use here, so relatively straightforward. And then we also have a motion frame. So this motion frame is for the impeller, and let me hide the SPH elements here. It's for the impeller in the shaft. We also have baffles around the tank. So basically this configuration allows us to model water as is being added into our domain and then partially filling the tank and being mixed by the action of the impeller. So basically we incorporated the motion frame. We linked the motion frame here to the impeller and to the shaft. And I can show like where how the frame is configured. So we have a relative position for the frame motion, as well as basically rotation set up for it. So it's basically set to rotation with a fixed angular velocity of 20 radians per second for this simulation. And it runs through the whole course of the iteration of the simulation. We have a 10-second simulation as set up in the solver. So if we continue going down through the data tree, we can see the geometries that have been imported. We have the impeller, we have the tank body, we have the inlet, and we don't have any outlet for this model. We just have an inlet, which is the only surface here for the model. And all of the other geometries are imported as walls. So we have the four baffles as well on the sides. And yeah, that's pretty much it. And for heat transfer, I assigned the tank with a temperature. So to do that, if you go right into the tank, we have wall. Let me increase this a bit. So we have a wall here on the tank, and then we have these different tabs for transform, mass. Nothing really to change here once you import the geometry. And then for thermal, you can specify either as adiabatic, so no heat transfer, or you can prescribe a temperature. Here I prescribe the temperature of 0 degrees C or 273 Kelvin. So basically that means the walls of the tank are going to have a constant temperature, and they will be able to exchange heat with the incoming fluid, that's water, that added as a hot fluid at 90 degrees C, which we do it right here actually. So here we have the basically the mass flow rate of water, 4 tons per hour, and there it is added at 90 degrees C, and you can change the units to whatever unit you prefer. And the time is so basically water is added from the beginning, from time 0 all the way to 4 seconds, and then we stop after that and let the tank, the impeller, mix the contents of the tank, the water, and we will see how the temperature evolves over time for the fluid phase. So that's basically it. So we don't have any volumetric inlets for this case. We only have inlet coming from the inlet surface. And I've also implemented some user processes, like for the water surface, for example, which we will see the results. Um, yeah, so basically that is it for like the basic setup for the simulation. If I run this for a while and I will enable the view of the SPH elements, you can actually visualize the water coming in. Note that here for the SPH elements, I have a stride of 10, so I'm not really showing all the elements. There are more elements, but I made the nodes relatively large so that we can see them individually a little bit better. So as water pours in and it's colored by temperature, you can also color by the velocity or um, other variables. But I want to see like how the temperature of the fluid elements change over time. So you can see hot water, and then once it encounters the walls of the tank and drops down, you can start to see that the temperature drops. So this may take a bit of time, so I'm going to just jump through some of the time steps so you can see water pouring down and cooling, especially on the walls, like a greenish temperature color indicating a lower temperature. And then once we close the water inlet at 4 seconds, that's how much water we have left, we have in the tank. And then we don't have any water being added anymore after that. And then we can go, say, around 7 seconds, so you can see that the water now, everything looks kind of yellow, a little bit of faint red. And then if you go to all the way to 10 seconds, you can see that it's now yellow and green, indicating that the temperature has dropped. So there are other ways you can visualize it numerically using different plots, for example. So Ansys FreeFlow has a lot of useful post-processing capabilities for plotting as well. So one of them, for example, is the temperature here. So you can plot the temperature of the SPH elements, and using the count fraction in percent here, we can visualize like what elements have the most like predominant temperature. Um, we could also visualize the time evolution for temperature. So I click these ones, and you won't see much because it's recalculating them here, generating the statistics curves. But we can also, in the meantime, try to visualize other plots. So this is at exactly 10 seconds of simulation. So this is a time specific. So um, let me uncheck these ones. And then what we see here is the velocity distribution versus radial distance. So I created a custom property called radial distance, which is basically the distance from the center of the domain for each SPH element. Um, and then I plotted the velocity profile for these points, so you can see how the velocity changes. So we have a high velocity in this region, which is possibly closer to the impeller. But as you go closer to the walls, as you go further away from the center, your velocity tends to drop. We can also visualize the temperature versus velocity plot. So basically showing like um, how much velocity each element has and how much temperature each element has. So these are useful cross plots showing the relationship between the two, if there's any. So you can definitely see that there is some high velocity particles that have a relatively high temperature, um, whereas usually lower velocity particles can have high and also some low temperature as well. So it can be a bit complicated to judge by just looking without doing more complex analysis as well. So I have another cross plot here that I want to visualize, which is the temperature versus the z coordinate. So the z coordinate is the vertical coordinate. So what I'm basically looking at is how the temperature varies as you go, as you change your depth through your domain. Um, so basically, we can see that at lower depths, close to the bottom, we can have quite low temperatures, and at um, as you go up, you tend to have generally um, higher temperatures. Um, so there's more colder particles near the bottom, and we can actually visualize that here in our uh, in the 3D view. We can actually see that there's a lot of like bluish elements indicating it's cooler here in the bottom, which might indicate as well that mixing is not that great possibly. We could try to improve the geometry or speed up the rotational speed of the impeller or do something else to try to prevent like cold spots, areas where mixing doesn't seem to be that great. So yeah, so I have my multi-time plots as well. So here I just plotted the average turbulent viscosity in purple color, and then we also have the mass of water into the tank. So it's a bit more than 4 kilograms, 4.5 around kilograms of water that we add, and then we stop at 4 seconds, and then we have just a constant value. And then for turbulent viscosity, we can see that the mixing is quite intense in the first 4 seconds, and then it kind of drops afterwards. Um, so, and the turbulent viscosity axis is here, the secondary on the left side. And here I'm just showing the variance of to show like basically the variance of different properties like velocity of the particles and temperature, and they seem to follow similar trends, indicating that the temperature is tied with the velocity of your fluid overall, with the variance especially. So um, basically, these are some of the useful tools that we can use to understand better, and there are more, of course, uh, useful tools that we can use in Ansys FreeFlow for both pre-processing, post-processing, in cases where we have heat transfer between the walls of a domain of a geometry and the SPH elements. So if we want to do more advanced and maybe more realistic views of the fluid and integrate other parameters, maybe one of the useful tools that Ansys has is the Ansys EnSight. So I'll open the model in Ansys EnSight. I've already opened it. So to do that, you have to go into your simulation file that was generated from FreeFlow, and there is a .rocky20 file that you can open up, and that will you'll be able to manipulate the SPH elements and look at different properties. Here, for example, I have the SPH elements enabled, and if you're not familiar with EnSight, I would highly recommend going through tutorials on it. So the SPH elements here are colored by temperature, and there's a lot of different controls. If you go into edit, you can see, for instance, basically the SPH as it's imported from FreeFlow, and I can also create some very useful what is called ISO volumes as well. So I will disable this, and I will, to make it easier to visualize, I will disable the tank. And then you can see here that I'm coloring everything by turbulent viscosity. So this is a view of basically the turbulent viscosity. And we can see that areas close to the impeller have a relatively high value. I can disable the legend just to make it easier to visualize and separate them. So turbulent viscosity uh, is higher near the impeller. We can also visualize velocity as well. So we can see velocity higher near the impeller as well, and temperature profile. So this temperature is around at 5 seconds. If I go further and let it calculate, we can see that the temperature has changed. So we have cooler temperatures near the bottom of the domain, and warmer temperatures surrounding. So yeah, so with SPH we can do, sorry, with FreeFlow we can do all kinds of visualization. So here I can change the color to something that to either a variable, or I can make it constant. So for instance, I can make I can set the color to say kind of a light blue to make it look more realistic like water, or maybe change the transparency. So to do that, I could go into edit, and if I click on advanced, we have the general options here. So there's a lot of different options, like the opacity to make it either more transparent or less transparent. I can change that, and it will automatically change because I'm not delaying updates. And uh, here for node, the key thing to make this kind of visualization for liquid is to display the SPH as a screen surface. We can display as spheres, but the screen surface kind of builds a surface based on the SPH elements and gives it a more realistic water-like, fluid-like view. So if we also increase the scale by the size, we can either make it a function of a variable or not. We can vary that scale to, we can basically make it even smoother. And one thing that is also useful here is when you create the ISO volume, you can basically use a variable to constrain where you want your ISO volume to be. So basically, I chose a neighbor account, which for the SPH is related to like how many neighbors each element has around it. So here I want to pick elements that are close together, not the elements that are far apart. So basically, if I choose like the lowest number, which I believe is around 24 or 25, you can see not much of a difference at all. Um, but if I go to the point where we're injecting, you can see we have a more uniform, sort of slightly more uniform, and I can actually make it bigger. Then we can see that we are now basically removing a lot of the SPH elements that have a low neighbor count. So I will set this back to 30, and then once we have set this up, we can basically rotate it around to get a better view, and we can also record animations as well. Going to basically, you can export an animation here, and you can select how many frames you want. So for here, I'm starting from basically frame 200, but I can actually start from frame 0. Likewise, and go back where I have no fluid yet in my tank. So this provides a lot of useful tools to actually visualize your fluid flow in a more realistic way, especially for animations, especially if you're doing a presentation or something like that. It's fairly helpful. So yeah, so this is these are some of the tools for pre-processing, post-processing for Ansys Flow with EnSight. So thank you so much and have a nice day.